Hey guys, welcome back to chapter 18. We're going to move forward into a new concept in this chapter. It's still entropy related, but we're going to expand this idea a little bit. So, first things first, I told you that the second law of thermodynamics is that the entropy of the entire universe is always increasing, so it's always dispersing, it's always becoming messier. Determining the entropy of the universe. Yeah, that's nearly impossible to directly determine. That's a hard one for us to figure. So we saw that determining the entropy of a system, that's pretty easy. But then determining the entropy of everything else outside of that system is pretty impossible. It's hard to determine. So entropy of the universe, impossible to determine directly. So we needed a different way to study this idea of entropy and determine if something is spontaneous or non-spontaneous. So we can look at a system, but if we don't know what's going on in their surroundings, we can't determine if that's going to happen without extra input. So chemists and physicists came up with something called Gibbs free energy. So Gibbs free energy is defined as a state function that relates enthalpy and entropy, and it helps us to determine spontaneity. So once we determine the value for Gibbs free energy for this delta G, we can then determine if it's spontaneous or not. When applying this to chemistry, another way we can think of delta G or Gibbs free energy is we can think of it as the chemical potential energy. So chemical potential energy. So that's one way that we can define it for our usefulness. So what is Gibbs free energy? What is potential energy? Well, potential energy is the energy that is stored up or the energy that is available to do work. So if we store up energy, that energy would then be useful to do work. So the maximum amount of work energy that is released into the surroundings during a chemical reaction. And then again, just for ease, we're talking about a system that is at constant pressure and constant temperature. So remember, that was one of the guidelines for enthalpies, is to be at constant pressure. Okay. So what is this Gibbs free energy? It's going to tell us about the spontaneity of that chemical reaction. So because the entropy of the universe determines if a process is spontaneous, we can use Gibbs free energy to also determine if it's spontaneous or not. So Gibbs free energy, a little bit easier to determine than the entropy of the universe. Okay. The other relationship that we have to point out at this point, and it's probably something that you'll want to write down, is that Gibbs free energy and the entropy of the universe are inverses of one another. So when delta S is a positive number, entropy is increasing, that's spontaneous. For G, when delta G is negative, that is also a spontaneous reaction. So here's where that definition of Gibbs free energy being potential energy is useful, because we want to lower the potential energy. So the whole purpose of chemistry is to gain stability, to lower the potential energy. So lowering the potential energy would be a spontaneous process. Okay, and vice versa. If this universe is becoming more organized, that's negative entropy. And if we're increasing Gibbs free energy, if we're increasing the potential energy, that's also a bad thing. So cleaning is bad, and increasing potential energy is also bad. So just know that those are inverses of one another. One's positive and one's negative. Okay. So getting to know Gibbs free energy, we typically write this equation without subscripts just because it is a bit cumbersome to write the subscripts. But just know we're talking about Gibbs free energy of the system, enthalpy of the system, entropy of the system. For Gibbs free energy, if the process is negative, so if delta G is negative, that means that delta S is positive, and that is a spontaneous reaction. So it's increasing or becoming more dispersed. We're lowering the potential energy, and that is a spontaneous process. If delta G for the process is positive, the delta S for the universe is going to be negative, and that is non-spontaneous. So if we are cleaning up, that's non-spontaneous. Or if we're increasing potential energy, that is non-spontaneous. And if delta G for the process is 0, that means there's no net change to that system. No net change to the system. Okay. So I've talked about Gibbs free energy. I've talked about how the signs relate it to spontaneous versus non-spontaneous. Well, now we need to know, well, what is this free about the free energy? So the free energy is the maximum amount of energy released from a system that is available to do work to the surroundings. Well, what kind of work would we want to do with energy? Well, we've got things like car engines. We've got things like jet engines and fuel cells and water wheels. So those are the types of things that would give us a Gibbs free energy that would release energy from the system and would allow us to do things like drive our car or fly a plane, or use it as a battery in some case. Okay. So what is free about this Gibbs free energy is it's free to be used somewhere else. So some of the energy in a system would not be free to be used by the surroundings. Some of the energy would go to increasing entropy of the surroundings. So it would be going to making things messier, to dispersing the energy. So it's not available to us to do work. It's not available to drive our car because it may be turning liquid into a gas. So we wouldn't be able to use it to drive our car because it's already being used up for a state change. Okay, so that's one example of not free energy. Some of the energy may be used to heating things up or lost to heating things up, if you will. So if you think again about a car engine, those engines get pretty hot as you're driving your car. Well, heating up an engine block is not going to be useful to us. Heating up an engine block is a scenario where we lose energy to some other side process. So that energy would not be free energy. We cannot use it to do work because it's used somewhere else. So if we think about the efficiency of different things that I talked about, the efficiency or the amount of energy stored up in a car engine, car engines are about 30% efficient. So 30% of the energy that create is actually available to do work, to move the car. The other 70% is used up who knows where. When we have something like a water wheel, now we've got 90% efficiency. So we don't see a big increase in the heat there because water's it's got a pretty high heat capacity. We see a little bit of it probably going to the surroundings to increase the entropy of the surroundings. But for the most part, our water wheel is about 90% efficient. So 90% of the energy that we create, we can use to do some work. 10% is used or lost somewhere else. So when we talk about this free energy or the energy that's available or being given off, we're talking about the energy that's being released to do work in the surrounding area. This is a really great video. So it's also in your video links. I think Bozeman Science does a great job with this chapter. So you can either get into this slideshow and click on this link, or you can just go to the video links in Blackboard and you'll see the Bozeman Science videos there as well. But I just think it's a really cool video, animated video, to help you out with this idea of Gibbs free energy. So looking at this equation, I've talked about almost every variable here, right? I talked about Gibbs free energy, tells us about the spontaneity. Change in enthalpy is how the heat changes. Change in entropy is the increase or decrease in the dispersion or the messiness. I haven't yet talked about this T here. Oops. That T piece is the temperature here, okay? So temperature certainly is a factor in determining the spontaneity of these chemical reactions, okay? So what we can do with the formula that we have and what we can do with this temperature is we can calculate if a reaction is going to be spontaneous at a given temperature. So we want to calculate delta G at 25 degrees Celsius and determine, is this reaction spontaneous or non-spontaneous at 25 degrees Celsius? Okay. So let's take a look. All right, so our formula is delta G equals change in enthalpy minus temperature times the change in entropy. Okay. In this problem, they've given us some of the variables. So they've flat out given us entropy. They've flat out given us, enthalpy. They've flat out given us entropy. One of the biggest mistakes that I see here, and I left the units the way that they were, is enthalpy is typically given in the units of kilojoules, and entropy is typically given in the unit of joules. I don't care which one you choose to put into this formula, but just know that you have to use one or the other. You can't use kilojoules in one place and joules in the other. They're not the same thing. That's not apples and apples. So in this case, you've either got to use kilojoules and kilojoules, or you have to use joules and joules. I typically use kilojoules just because I'd rather deal with decimals than ridiculously large numbers, but again, it doesn't matter at all. The other unit you need to keep an eye on is this guy right here. So I've given you the temperature in Celsius, but looking at the unit for entropy, what unit do we see? Yeah, we see Kelvin. So again, I can't use Celsius in one place and Kelvin in the other. I'm going to have to pick and choose where I use that. Okay. All right, so let's plug and chug into this equation. So delta G is going to be our enthalpy. So that's going to be 95.7 kilojoules minus temperature. So I'm going to have to put this in Kelvin. So 273 plus 25 is going to give me my temperature in Kelvin. So 273 plus 25 equals 298. So 298 Kelvin. And then I've got to put this into kilojoules. So I'm just going to do this one time. We got joules on bottom, kilojoules on top. In 1 kilojoule, there are 1,000 joules. So I'm going to divide 142.2 divided by 1,000. And that's going to give me 0.1422 kilojoules per Kelvin. Okay. And what we see here is our units are going to work out for us. So Kelvin and Kelvin are going to cancel. So I'm going to add and subtract kilojoules here. And Gibbs free energy is a measure of energy. So the units are kilojoules. That is super duper convenient for us. Okay. So let me first take 298 times 0.1422, and that gives me 42.4 kilojoules. So 95.7 minus 42.4. So delta G equals 95.7 minus 42.4, a positive 53.3 kilojoules. Okay. Is this a spontaneous or a non-spontaneous process? Delta G is positive. We're increasing potential energy. So this would be a non-spontaneous reaction. We would have to continually input energy into the system in order for it to take place. I hope you guys found this helpful.